Okay, in this video I'm going to solve this problem, which is basically some basic definitions of set theory. And in this problem we're given a few sets to work with. We're given the set capital A with the letters A, B, C, D, E, F in it, the set capital B with the letters A, C, E in it, the set capital C with D, E, F, 1, 2, 3 in it, the set capital D with A through Z in it, lowercase letters, and finally the set E, which contains 1, 3, 5, 7, ... In other words, up to infinity of the odd integers. And the ellipses repeat the pattern in both sets D and E. D is a finite set. There's 26 elements, but E is an infinite set. Okay, so what I'll do is I'll go through and write out these solutions. Part A, I'm interested in A intersect B. And the intersection includes those elements that are in both. And so we are writing out the elements of these sets. So I'm going to go ahead and write A intersect B equals, and I'm looking for those elements that are in both A and B with the intersection. And it looks like A, C, and E are in both, and so that's going to be my intersection. Okay, for part B, it says let's find A union B. And now this means we can just take all the elements of A, list them out. This is A union B is all those elements which are in either A or B. So I can list out all the elements of A first. And then I'll add any elements that are in B that weren't already there. Well, B only has A, C, and E in it. They're already in there. And so there's what we have. Notice that ACE is equal to B and the ABCDEF is equal to A. Anytime we have the intersection of a set with another one equal to one of those sets, then I can say that happens if and only if B is a subset of A. We can also say that if the union is equal to one of the sets, then one of them is a subset of the other. And that's the case we have here. B is a subset of A. And so both of these things come true, and you can see it happening right here. For part C, it says, let's write out the elements of A intersect with C. And A intersect C. I'm looking for those elements that are common to A and C. Think of it as the overlap. A has A, B, C, D, E, F in it. And C has D, E, F, 1, 2, 3. And we can see a clear overlap on the three elements D, E, and F. Part D says write out the elements of B intersect C. And now we're looking for the overlap of sets B and C. B has A, C, and E in it. C has D, E, F, 1, 2, 3. Is the A common? No. Is the C common? No. Is the E common? Yes. Okay. So it's just the element E. All right. So I'm just applying the definitions of union and intersection. Here now for part E, it wants me to do a set difference. Is A minus B equal to C? Well, what I'm going to do is I'm going to write out A minus B. And I'm going to take all the elements of A that aren't also in B. And we're going to therefore subtract out the elements A, C, and E from the set A. And I'm going to be left with the B, D, and F from set A. Okay? So I subtracted out those elements from A that are also in B. For part F, it says, is it true that D minus B is a subset of B? D minus B. Let's just do it. Let's figure out what it is. Probably isn't, because I've taken out from D all the elements that were in B. So how could what's left over be a subset of B? I think it could if everybody's the empty set. Some special cases with the empty set. But in this case, D minus B, D is all of the letters, A through Z. B has the A, C, E in it. And so D minus B doesn't have the A, C, or E in it. So it starts with B, A, B, C is not in it, E is in it. No. A, B is, C, no, D, yes, E, no, F, G, H, and so on are all in it up to Z. Okay, so it's a subset of the alphabet, and it's certainly not, D minus B is certainly not a subset of B. And did I answer the question on part E? I don't think I did. A minus B is B, D, F. Is that equal to C? No, it is not equal to C because C has D, E, F, 1, 2, 3. A minus B, A, C, E, B, D, F. Yeah, it's not equal to C at all. Part G asks us, is it true that E minus D is the empty set? Well, let's look at what E minus D is. All those elements of E take away those elements which are also in D. E is 1, 3, 5, 7, the odd numbers there, and D is A, B, C, A through Z. So if I do E minus D, taking out the elements of D doesn't do anything because none of them are in the set E, so it's E. Okay? And this is not equal to the empty set, so the answer is no. And the answer to E was no also. G, H is A subset of D? A is A, B, C, D, E, F. D is A, B, C, D, E, F all the way up to G, and the answer is yes. All elements of A are also in D. Okay, so hope that helps some basic set theory problems.